A microscopic sliver of quartz rock vibrates 24 million times a second inside your laptop. Without this stone, the machine is completely dead. Every computer on Earth relies on a piece of analog nature to function. Hardware engineers call it the clock generator. Jacques and Pierre Curie discovered the piezoelectric effect in 1880. They squeezed a crystal and measured a faint electrical charge. The brothers reversed the experiment. Electrical voltage shocked the crystal. The rock bent outward and violently snapped back to its original shape. Modern processors hijack this exact physical movement. Inside your computer case sits a silver vacuum-sealed cylinder. The cylinder measures just 2 millimeters across. An electrical current hits the quartz floating inside. Quartz distorts under the current. Physical tension forces the crystal to spring back. That snap releases a tiny voltage pulse into the motherboard copper. This single pulse hits a clock multiplier circuit. The chip multiplies the rhythm and broadcasts it to every component. Processors receive the beat. Memory modules catch the rhythm. Graphics cards sync to the pulse. A computer contains millions of separate microscopic parts. They are completely blind to each other. If RAM sends data 1 nanosecond before the processor is ready, the system crashes. Data collides and corrupts instantly. The quartz acts as a universal metronome. The frequency enforces a strict grid of time across the entire motherboard. Every single calculation must align to this physical beat. You press the letter A on your keyboard. A switch closes. An electrical voltage races toward the processor. Processors refuse to accept the signal immediately. Silicon chips wait for the exact edge of the next quartz pulse. A microscopic electrical wave arrives. Logic gates lock the data into a register. Silicon pathways then move the data into memory. A 3 GHz computer relies on a multiplied rhythm that ticks 3 billion times a second. Heat ruins this timing. Quartz expands when your laptop gets hot. The rock physically grows. Vibration speeds drop. Engineers developed a solution called the AT cut. They slice the quartz at an exact 35-degree angle to the crystal lattice. This specific geometric cut resists temperature expansion. Robots seal the rock in a vacuum, so air friction never slows the snap. We think of computers as pure mathematics. Society imagines lines of code existing in a weightless virtual void. They are actually physical machines bound by atomic limits. When a computer program suddenly freezes, you are seeing a timing failure. A signal missed the clock pulse by a fraction of a nanosecond. The electrical charge vanished into the silicon. Transistors now shrink down to 3 nanometers. The speed of light becomes a massive engineering bottleneck. Electricity travels roughly 1 foot per nanosecond through copper. A clock pulse takes real time to reach the far edge of the motherboard. Motherboard designers literally bend the copper wires into zigzag patterns. They force the signals to travel identical physical distances. A straight wire would deliver the signal too early. Total synchronization prevents catastrophic data failure. Every email you send rides on a vibrating rock. Online banking transactions wait for a quartz pulse. Your digital life remains chained to an analog piece of the earth. Engineers pull a crystal from the dirt. Lasers slice the raw material. Machines solder the piece to a silicon board. The crystal beats millions of times a second until the machine dies. The next time a loading screen appears, remember the mechanics. The machine is just waiting for a stone to snap back into shape. Physics always governs the mathematics. I investigate the hidden engineering secrets inside everyday objects. Subscribe to see the mechanics of the modern world.